So last time I started discussion of the Chernoff bound, which is a useful property for the so-called independent identically distributed variables, and we assume that this property holds for the quantum measurements when you run the same algorithm many times and make probabilistic measurements. But it is also something which is applicable to a much wider context, and it is used heavily in statistics. In some sense, it's a complementary property to the central limit theorem, where central limit theorem tells you how quickly the distribution converges towards the mean, and it gives you a measure of the variance, which is the width around the mean. Chernoff bound gives a measure of what is in the tail. So it's other side, but both of them have their own uses. So the situation which we are looking at had this variable which I called xi, and they had only two eigenvalues. They are essentially polymatrices, so they are +1 and -1. And the notation which I used is the mean of these variables is 2p minus 1, where p is the probability of +1 and 1 minus p is the probability of -1. And to simplify writing, I will just denote this mean as mu. The other thing which is important is what is called the sample mean. This is the complete expectation value over the whole distribution, but sample mean is the result of a finite number of measurements. Let it be called M, and the job is to find a bound on how accurately the sample mean approximates the exact mean, which is the expectation value. And that is the property of the Chernoff bound. So what we are after is the probability that this we call x bar. So probability of x bar minus mu is larger than some quantity, where delta is a range which determines the tail, how far away you are from the mean. And when you are far away from the mean, your estimate will be wrong. So this is in some sense measures the instances where there is an error. Okay. So this was converted using Markov's inequality, which is basically putting everything in the exponent, and I derived the consequence of Markov inequality as this is less than or equal to the expectation value of e raised to xi times e raised to minus ms mu plus delta. Okay. So now the next job is to calculate this quantity accurately. This is proportionality constant is S. There is no sign here. S always taken 0. So S is greater than 0, delta greater than 0. Okay. Then this Markov inequality works because exponential is a monotonic function and it's also always positive. So what is the expectation value for this? You can calculate it for one variable and then take the power m. So e raised to s xi expectation value is p times e raised to s plus 1 minus p times e raised to minus s, and this was bounded by again putting things in exponent. Okay. So this is what I wrote down in the last lecture, and now the job is to tighten the bound as much as possible. So we minimize the bound as a function of s. So you have to take this whole quantity. What this is this whole thing raised to power m, and that number can be handled reasonably well. Looks a little complicated, but it's not that bad. So this quantity is e raised to minus ms. That is this part. Then this is e raised to mp. That is this part, and then there is this. So you have to essentially take a derivative of this whole thing and put it equal to 0. Now again the exponential is monotonic, so taking a derivative of this and putting it to 0 is equivalent to taking just a derivative of the exponent and putting it equal to 0. So let me just do that, and that derivative of the exponent will give minus m plus derivative of this with respect, which is 2mp e raised to 2s, and the derivative of this with respect to s is minus m times mu plus delta. So now things can be solved, which is gives e raised to 2s. This m is common everywhere, so it can be ignored. Then there is a 1 over 2p from this. This goes to the other side, it is 1 plus mu plus delta, and this can be written as delta by 2p because 1 plus mu is equal to 2p. That was notation here. So this gives a tightest constraint on the right hand side, and now we can write down what this whole structure is by substituting this particular value inside whatever you minimized, okay, which is this, which is substituted for that. And that can be done. You have to, so this is a result for so-called positive tail. It has certain constraints because the sample mean, whatever it is, it cannot go outside this interval. It can be only between +1 and -1. So this delta is not going to be arbitrary far away. It will be only within certain limits, and the range of delta in this particular case is kind of, so this one is 0 less than delta. You can put equal to sign also if you want, and 2 times 1 minus p. So in this particular range, you find this, substitute all these things inside it, which gives probability x bar minus mu greater than delta is less than equal to count everything to the various powers. So you have to substitute in this e raised to 2s is, you can write it different ways. So let me just, okay, save some writing here. Let me call this object by a new symbol. I'm going to call it omega, delta over 2p. So now this I have to substitute with various identity, and some parts actually simplify. So I think ms 1 plus mu, or 1 plus mu is at 2p. So I will just do it in multiple steps. So e raised to mp, this quantity is omega. E raised to 2s minus 1. Okay. Now this whole stuff is e raised to minus ms, or s I have to substitute. So well, I will take out some factors. So ms plus ms mu is equal to 2p. So it is e raised to 2 minus this and this. You have to basically, let me see, simplify. Minus ms mu plus delta is equal to minus m. 1 plus mu is 2p s, and then minus m s times 2p omega delta is equal to 2ps. Point was to get e raised to 2s back again, because e raised to 2s is 1 plus omega. So I can put all these things together. So it will become e raised to 2s, which is equal to 1 plus omega times e raised to 2s times mp and it's missing something. Let me correct it properly. So this is all in the exponent. E raised to 2s is 1 plus omega. Then the mp is also a common factor. So it is 1 plus omega, okay, times a minus sign. Okay. So what did I miss here? Let me get it back again. So I was trying to simplify the structure. E raised to mp omega, that was the first part. And the second part, there is a negative sign, so it goes in the denominator. But other than that, e raised to 2s is the result looks like this: 1 plus omega raised to power 1 plus omega times mp. Okay, I think that is the expression which I wanted. So yeah, it's written more commonly as so this is the sort of well-known expression for the Chernoff bound. Probability is all converted into powers, where the number of trials goes in the exponent. That is what we want. It has to be exponentially suppressed, and this all the intermediate stuff, whatever is happening here, this p is related to the exact mean and omega is related to the deviation from the mean in a certain sense. So this is the standard expression. Now it can be simplified. It kind of looks messy, but by using certain properties of the logs, you can simplify this thing a little further, and that depends on the application, etc. And I will choose one particular version, but the standard textbook version of Chernoff bound will have this kind of expression. There is a similar expression for the negative tail. Which is kind of easy to guess, but the range of delta there is a little bit different. And what you want in this particular case is a x bar minus mu is less than minus delta. So the other side of the distribution, delta is a cutoff, and x bar is way away from the cutoff. That's what this means. And the result is not too complicated to guess. And that is essentially change in sign of omega. So all we need to do is take delta to minus delta, and the only place it appears is this omega, it flips a sign. So you can work it out, but it doesn't give you any new algebra in terms of calculation. Okay. So these are the distributions of the two tails, and if you want a total result, you have to add the two contributions. How much is in the positive tail and how much is in the negative tail. It will give the total probability of error. Okay. So that can be done, but again using a certain approximations or other logarithmic inequalities. We need different versions on both the sides. And I will just write down the expressions which are needed. Is one of them is log of 1 plus omega is bounded by this is the positive side where omega is positive, well, much more than that. Omega is in this range. Okay. So, I mean, you can kind of see it by Taylor series expansion, but the bound is exact. Taylor series expansion will give log of 1 plus omega is omega minus omega squared by 2 plus omega cubed by 3. You can get something from doing a expansion of this. So first two terms will correct, but this is rigorously true much more than that. Let me just put omega greater than 0. But it's bounded. And the other one which you need is a slightly different one. So I will write it log of 1 minus omega, but multiplied together with this extra factor, and that is greater than equal to minus omega 1 minus omega by 2. This is for omega less than 0 side. Where are these logs going to appear is you are trying to simplify this answer by writing it e raised to 1 plus omega times log of 1 plus omega, and this will be e raised to 1 minus omega times log of 1 minus omega. So everything is put in the exponent, and then you simplify the exponent by this particular identity. This overall power of NP is going to remain outside. Okay. So now if you do all this substitutions, so this is the positive tail, the expression, all this thing will simplify to I will write down various factor e raised to omega times this thing in the denominator, so it will have a negative sign. But I will put this factor for log, so minus 1 plus omega and then log is bounded by this, so I will write as omega divided by 2 plus omega, and there is a 2. We are just rationalizing this quantity, which kind of looks correct, okay, and then various things can be simplified by adding all those things together. Actually, there are some cancellations why all these factors are used. So if I take a common denominator, this will become 2 omega plus omega square. Some part will cancel out with this quantity, and the result looks like e raised to minus omega square by 2 plus omega raised to. Yeah. One of them, 2 omega, will come and cancel with this, and omega square survives. So this is one of them. Then the negative tail, a similar thing will go on. So it will be e raised to minus omega is here, and this whole stuff is in the denominator. So there is a negative sign and it comes once more again, so it becomes plus. The point of doing all these things is to get the same exponent in both cases, and this is e raised to minus omega square by 2 times mp. And so now we can put all those things together, which is the final result for the total distribution on tail. I am adding the two results, so the probability now has a modulus sign. And that is 2, I'm adding these two numbers, 2 raised to minus mp omega square by 2 plus omega. There is no 2 plus omega here, but 2 plus omega is always bigger than 2, so you can write a combined expression which looks like that. So this was the point of the whole exercise. You want to get some expression which has this m in the exponent. Because what now is required, that this quantity, I want to put a bound. This is the error. So when it is, this is in some sense the failure probability. So now I can say that for this failure probability less than some epsilon, it is going to be a function of m. What I want is, this is the upper bound on it. So it will tell you what the result is. Well, all I have to do is, since it is an exponent, take a log to get a bound on m. And m has to be bigger than because of the negative sign. And log of 2 by epsilon m 2 is this one, this is epsilon m on the other side, and times 2 plus omega by omega square. There is a p somewhere. And you can simplify this thing, write it in the notation of delta should be the same as this. Omega is delta over 2p, and there are some cancellations inside here. Eight p plus delta divided by delta square, I think. Yeah. This is omega square in the denominator. Okay. So the point was essentially to get a bound on M, which depends logarithmically on the error. That was the whole point of the exercise. We did not want a power law dependence, but a log dependence on the error. And so this becomes an efficient algorithm from that point of view. Okay. There is a little bit of a caveat, and that is because dependence on epsilon is log, but dependence on delta is power law. Okay, so delta must be kept finite for efficient algorithm, because if delta goes to 0, we are back to the same problem. There's a power law dependence on the accuracy. Okay. And that can be is possible when allowed values are this is measured values of mu are kind of discrete, and then you can say that then one can take delta is half the separation in some sense. If all the values of this sample means which you are scanning are spaced in a discrete manner, then delta cannot become arbitrarily close to 0. They are discrete, so half the separation will work, and then the algorithm is okay because delta doesn't go to 0. This happens in digitized calculation where the values you measure are not actual continuous real numbers, but like finite precision arithmetic, you have whatever 16-bit, 32-bit, etc., whatever it is, they are all discrete values, and you truncate. The point is to make sure that even when you have finite delta value, the expectation value which you will get is useful. And as long as that is guaranteed, then this algorithm is good enough. But you have to keep this in mind. This discretization is necessary all over the place, and you should not ignore it at any stage. And now we can ask the total complexity. So there are three parts. One of them was number of components. This is a poly we had taken that O is made up of operators at k distinct locations, and the only non-trivial ones were where each location you will have either sigma 1 or sigma 2 or sigma 3, so that produces the maximum number of components is e raised to 3k. Then there is a small k which also appears. These are the number of qubits in circuit for every operator you measured. I illustrated with some circuit. Every qubit you have to take a Pauli matrix and apply a C0, take it to the ancilla, and there are k components, and so you have to count how many times C0 will appear, and that number is k. And then m is a number of repetition of algorithm which is due to probabilistic measurement, which is what I estimated here with all the Chernoff bound, etc. So the total effort is order product of these three factors. Good. You have to measure each one of these components which appear in the expansion of the operator one by one. For each measurement, or you have to repeat the algorithm so many number of times, and a single trial will require so many of the C0 operations. So the product of these three numbers, and this is well behaved. So this is efficient for the correlations or Green's functions, whatever you get, up to some finite number. 2-point correlation, 3-point correlation, some number, whatever it is there. As long as that is finite, you can express all these objects, and dependence is log in the epsilon. Yeah.
So that is capital K equal to E or 3K or 3 or
This. No, it is 3K because the operators have to be non-trivial. Everything which is identity doesn't contribute. So yes, when you write the all polybases, there are 4 factors which can appear: identity, sigma 1, sigma 2, and sigma 3. But the non-trivial result only comes from sigma 1, sigma 2, or sigma 3. Identity doesn't do anything. As far as it just gives a reduced matrix, it doesn't couple to everything else. So this is the job, but what we have is a probabilistic algorithm. So success probability and for success, every attempt must succeed. So you are making measurements for so many different polybasis components. So this is actually a strong constraint when K becomes large, because it will drop very fast. But as long as you keep this number K finite, it can be bounded, and the simple inequality is this holds for epsilon between 0 and 1, whatever it is. But this is bounded. So yes, it's a probabilistic algorithm, but you can get a bounded success probability as long as this number is under control. You can make epsilon much smaller than K in some sense. And the dependence on epsilon is only logarithmic. So you have to keep all these factors in mind, and then you have a complete analysis of getting an efficient measurement of any operator. The constraint is that the number of individual components which contribute to the measurement, you have to keep them finite. So this is as far as this whole analysis goes, and it is an instance which can be applied to the Hamiltonian evolution problem, because this was the last part of it. You evolve the state, and then you have to measure it, and you need a confidence in whatever answer you obtain. So this is actually as much as I'm going to say about Hamiltonian evolution. And now I want to move to a next topic. Yeah. Capital K is when you decompose this operator in Pauli basis, how many non-trivial terms are there? Sorry, I got a wrong number here. It's 3 possibilities at every point, so it will be there. It is this. Sorry, 3 possibilities at every point. Okay. So the Hamiltonian evolution problem essentially is a matrix exponentiation problem. Of course, with all the caveats about the matrix being representing some physical system and interactions giving rise to all the off-diagonal entries in the matrix, which we made sparse for doing an efficient calculation, etc. But there are lots of other problems which one can define, again in the context of linear algebra. And the problem which is in some sense related to the exponential of the matrix is finding the inverse of a matrix. And one can actually convert one to the another in some fashion, but it's worthwhile to just treat as an inverse problem on its own. Okay. So Hamiltonian and what is the common occurrence of matrix inversion? It is a solution of simultaneous linear equation which requires matrix inversion and some notation which can be inserted is the simultaneous equations can be written as Ax is equal to B. A is a matrix, X and B are some vectors. And its solution is thus formally X is equal to A inverse B. And the point is how efficiently you can solve it. The criteria remains the same, that exact inverse, well, in some cases it can be calculated, but it may be too what to call long or requires too much effort. You want to find shortcuts. Okay, so this exact solution is something which we learned in school. You have a set of linear equations, you eliminate one variable at a time between 2 equations and keep on going till you get only one equation, you solve it, and then you substitute all the way backwards. And that procedure is called Gaussian elimination. And there are related versions of it like LU decomposition and things like that, which are a little bit better, but they're all of the same complexity class. And how many operation it needs is So this I will take this in n dimension. So there are n components of the vector x. So A is an n by n matrix, and if you do the counting of how many steps which will be required for Gaussian elimination, it is order n cube. That is too large, and you want to find something simpler. Okay. So what is employed in practice is a so-called iterative methods. And they are useful for sparse matrices. So the point is that you want to bring this scaling down in some manner, and it helps if the matrices are sparse. I will give you standard results. These are all kind of well-known techniques, and you will find them in numerical analysis textbooks. I don't want to go into too much detail about that, but I can give you essentially the overall behavior. So what does this thing do? So they work in what is known as a Krylov space, which is starting with some case and then keep on applying powers of A in a recursive manner, going up to some power A to the R. And why this is convenient? Because for sparse matrices, you have good schemes to multiply a matrix times some vector. And that, okay, we have written it down, sparse matrix times vector is order d times n. D is sparsity. Just have to keep on multiplying each one by one. So this is complexity of one step, and then the question is how many of these things I need to generate to get some approximate answers, because this iterative method will only give you some approximate answer up to some accuracy, and the total complexity will be this thing multiplied by the number of power, whatever is R. That is the idea of all these iterative methods, and what they essentially end up doing is the convergence rate. Criteria appears. And it's going to have a series expansion in this manner, and how fast the terms in the series successively drop. And that depends on essentially on the eigenvalues of it. Because every time you multiply, the magnitude will decrease by whatever the eigenvalues of A for a particular component is there. So now you have to again pick some convention, because the equation is such that I can multiply the whole thing by a constant, and then I can say that the eigenvalue of A is multiplied by the same constant. That is overall scaling behavior, and that should not appear as a part of the algorithm. So I can easily say that I'm going to give a bound on the eigenvalues of A. The largest eigenvalue is this, and then smallest one can be anything. And the problem becomes worse and worse when the smaller eigenvalue becomes close to 0. So that's what we call singular point. And we'll assume that no eigenvalue of A is 0, because then you can't do the inversion. So there is a mathematical way of writing this constraint is defining a condition number, which I'm going to denote by kappa, is the ratio of the largest eigenvalue divided by smallest eigenvalue, and eigenvalue can have some signs or phase in general, so I will put a modulus sign. And what are the eigenvalues? Are these things are? They are the eigenvalues of the matrix A. So this kappa is in some sense the maximum magnitude of the eigenvalue ratio of the matrix you are trying to invert. You can scale the largest eigenvalue to be 1, then it will be 1 over the small eigenvalue, but this is independent of the scaling. So all these algorithms, all these iterative methods, they will depend on the condition number. So that describes how quickly the series will go to converge. And of course, we have the dependence on the epsilon, which is going to be the approximation, because the iterative methods are going to approach it slowly as a function of the number of power in some particular manner. And you have to ask the question, what are the dependencies of all these quantities in terms of the complexity, the dimension, the order of the power series, the accuracy which you want, and this kappa. So here are some standard results. That you can kind of guarantee that this series converges by reformulating the problem in a clever manner. That is possible because the ultimate result is just a linear function. So in general, a linear function equal to 0 can be written as a condition for minimizing a quadratic function, just the first derivative. Okay, so you can construct a quadratic function whose derivative equal to 0 gives you this equation. And then quadratic function have a nice behavior as long as the curvature is positive, that you can start somewhere and then just roll down the hill. Okay, that is something which can be achieved by these particular steps. You move slowly all the way till the minimum. You will take some number of steps to get down there, but that is something which can be generically done. So this linear equation can be written as minimization of a quadratic form. And many methods have been constructed based on this particular idea. Okay. So there is something which is called a minimal residual method, and it constructs something which by definition has a positive curvature, just a norm, quadratic norm of this, and R is this quantity, whatever you want to call it. It's called a residue. It's basically how far you are from the exact solution, and then this is a positive form. You calculate the gradient and go down, except that there are lots of gradient. You are working in an n-dimensional space, so you have to minimize along n different directions. And that is a place where all the tricks are needed to find the best way to go down the hill. And the method, the simplest one, is just doing this, and it works up to some level, but sometimes it also fails. It fails in the sense that you are trying to go down this quadratic form, but the direction which you are choosing has zero gradient. Okay. And then this algorithm, trying to minimize it, it stalls. It reaches some minimal value of R, and then the next gradient, instead of taking you down, is just going in a direction where the function doesn't change. That can happen if the directions are not selected properly, and this method essentially suffers from that particular problem. And it has an acronym which is I think it's called just min-res. So that problem is cured by a clever version of this particular form, and which is called conjugate gradient method. It's a very popular method. Standard library packages are available for applying this idea. And here, what is essentially done is the directions for minimization which you are choosing are cleverly arranged so that they are all linearly independent from everything else which went before. Okay, so minimization directions are that all the directions we explore, but they are by construction orthogonal to all the ones we have looked at the previous iteration. And when you do that, it has a guaranteed in n iterations, because that is the dimension of the Hilbert space. There are no more than n directions. So this is a rigorous property, and what it does is that every time you do this, and so it brings down this worst case from n cubed to dn times n, which is dn square. But you want, in practice, it's much better than that. You don't have to go all the way to find an exact solution by exploiting all the directions. You can do a much better job by a finite number of iterations. That is the point of the exercise, and that is where this condition number will appear. You will guaranteed convergence of this irrespective of the condition number. That is fine, but when the condition number is given some value, there are stronger results about how fast it converges. And that you can look at in various textbooks, but the result is that the convergence is exponential. And the quantity which is minimized is actually it's a slightly different quadratic form which is used. The trouble with this is that if you evaluate it, it has a square appearing indirectly in the calculation, and so the convergence depends on the condition number of a square and not of a. But you can write the same result and guaranteed the positive nature by using a slightly different quadratic form. If you take a derivative with respect to x of this quantity, it will still give you the same linear equation. But the advantage is that this function has only one power of a instead of two powers of a, which is sitting inside here. The caveat is that to be able to make this positive definite, here it was automatic. Here you need an extra feature that eigenvalues of a must be positive. And that conjugate gradient kind of assumes, and then you can actually literally show by various properties which appear in these orthogonality conditions how fast the algorithm converges. It's it's a linear combination of this power series, and when you optimize it, you'll end up again with analysis of Chebyshev polynomials. It's all over the place, Chebyshev polynomials. But you get a result, and I will only write down the result, which how does it scale. And that is that this remainder Rk, R is this quantity, the norm of this is less than or equal to my writing will have to distinguish. This is kappa and that is k. So I'll put some label k, right, a little bit differently. And this is kappa, which is the condition number. And what one can demonstrate that this is a generic inequality which depends on square root of kappa. Why square root of kappa appears is a result from that Chebyshev polynomial minimization. It comes with all the sine and cosine and produces the kappa. I will not go into that much detail, but the scaling property can be just extracted from this, that this complexity is order d times n where epsilon is essentially the norm of the remainder. How much is the error in the solving the equation? Okay. And this is a powerful enough result in the sense that epsilon is already inside the log. Okay. There is a power law dependence on this condition number kappa, but that you cannot improve any further. It makes it a square root, which is actually reasonable. Nobody has found anything better than this. And where did the square root come? Because you can just expand this in a Taylor series by assuming the kappa is much bigger than 1, and when you do that, you will end up with a root kappa, whatever the simplification of this thing gives you. And this d times n is just a matrix vector product. So this is the conjugate gradient algorithm complexity, and now one can ask, can you improve this behavior by some quantum technique? And first guess will be to convert this matrix, sparse matrix vector multiplication into superposition. Okay, this one is already well behaved, but this capital N can be reduced to the number of qubits, which will be log n, then you will have a speed up. It doesn't quite work that way. The reason being that this algorithm requires this orthogonality constraints, which means you have to calculate dot products. And the dot products have to be calculated reasonably precisely to get this epsilon under control. Now you have n-dimensional vectors. There is no simple way to calculate the dot products. You have to look at all the n entries. And you cannot do anything about superposition tricks to simplify the dot product. That's the constraint. So yeah, people first immediately say that we'll simplify this. It doesn't work quite that way. And you have to ask a question, what is possible? It's already came down quite a lot from this n cube. That became a first power of n. Epsilon is log, so it is okay. And this kappa is a new variable that appeared when you don't want an exact solution, but an iterative solution. Okay. So this is all the classical analysis, and we want to construct an algorithm which will, well, in some sense have various features similar to conjugate gradient, though it's not going to be quite the same, but we want to convert this capital N to small n. That is the point. So we want an algorithm which can be parallelized. When you have a parallel structure, then you convert it into superposition. So yeah, one more comment is that what if the matrix is not positive definite? So the method can be used in slightly modified form by I multiply this equation by a dagger on either side, which is identical, with the advantage that a dagger is now positive definite. So I can apply these ideas. But what happens then is some advantage is lost over here, that this square root of the condition number becomes condition number, because condition number of a dagger is square of the condition number of A. So this advantage which was over here kind of disappears if the matrix is not positive. But this is as much as people have been able to do, and nobody has found a better algorithm. There are different tricks which somehow reduce the proportionality constant in front of it, but the scaling variables are as much as what appears in the conjugate gradient algorithm. Okay. So now we want to develop a new method which can be worked in this iterative fashion, but somehow it gets rid of this orthogonality constraint, because I don't want to calculate dot products. And there are various ways of doing it. There is one algorithm which is referred quite a lot in the literature. I will erase some of this. Which goes by the acronyms HHL, just the three authors, and they use superposition and the eigenvalues are handled using phase estimation. But the penalty that is paid, then this n goes to log n because of the superposition, but log becomes a power. So you gain in one place, you lose in the other place, and for that purpose, this is not efficient. People keep on referring to it all the time, but by this complexity ideas, it's not something which is very helpful. So I'm going to describe a different algorithm which will be able to do both log n and log of 1 over epsilon. And this algorithm is based on another old technique, which is the Newton-Raphson method. It is generically labeled as a solution of some function equal to 0. Okay. You can make all the different functions. You can write this as ax minus b equal to 0. Whatever it is, you can plug it in, but it requires one caveat. So you should be able to calculate the derivative of the function. And if the derivative can be managed easily, this method converges fast. And the remarkable thing is it converges even faster than the exponential. It is a so-called second order method, which means that the number of significant decimal points in your answer double every iteration. In geometric series, you add one decimal point at every iteration. Here, the convergence is much faster, and that is generally not seen in many of the numerical methods. This one happens to be a kind of an exception. And the result can be quite dramatic, that how many decimal points are correct? It will go like 1, first iteration, 2, second iteration, 4, third iteration, 8, fourth iteration, 16, fifth iteration, things like that. So if you start with a 10% error, fourth iteration always going to 10 raised to minus 8. It's basically you run out of the register very fast. And whenever this method works, you need only a few iterations to get the answer. Okay, 2, 3 iteration, job is done. You don't have to do anything more. And Newton surprisingly used it because he had to calculate the orbits of all the planets. And no computers, nothing was available. So he wanted a fast converging method, and he basically came up with this particular idea. It's a very simple construction, and what it does is at every xn, so you calculate what this thing does, f prime x is actually just the slope, so it draws a tangent, and all you need is a value of the function and its derivative. So let me now convert it to the problem of finding an inverse. Okay. So I have to choose a function. So I will first just work with numbers and let function be this, or what I'm interested is in finding the reciprocal of a number. The iteration is very simple. I just have to calculate the derivative of this. Happens to be minus 1 over x square. So it is a multiplication by x square in the numerator, and all that happens are just terms getting rearranged. So the result looks like this. Two terms will remain in the numerator. One of them, x square multiplied by this, just adds on to this, and the other one is x square coming from reciprocal of this, multiplying whatever is a. That looks like that. There is a reason why I wrote it in this particular manner, and the reason is that this is the identity for numbers. When I deal with matrices, this is the order in which they will appear. Okay. So but that I will describe in more detail in the next class. But just let me give a practical utility of this particular simple expression. In our whatever computer or even calculator, what is the algorithm for division? Addition and multiplication you do all the time. Subtraction is not very different. You have to just flip a sign and add it. How do you divide? And there is no arithmetic formula which allows you to divide. What all computers do is actually multiplication by the reciprocal. And then the question comes, how do you calculate reciprocal of a number? And well, there are various tricks, but the easiest thing to imagine is you don't want to calculate reciprocal of a arbitrary number because it will take too much time. So you express the number as some bounded value multiplied by an exponent. You just shift the decimal point. So it will always be integer within the first range of the decimal value multiplied by 10 raised to something. And then the reciprocal of 10 raised to something is very easy, 10 raised to minus that. So then I'll need to find a reciprocal for all the numbers, say between 1 and 9.9999, whatever it is. The computers actually, you are using a binary system, so you need to find a reciprocal of a number between 1 and 2. As long as then you have an algorithm for division. So how do you find a reciprocal of a number between 1 and 2? Well, again, the generic thing is function is given in some interval. You can always approximate by a polynomial, as long as the function is smooth. So you don't calculate 1 over x, you will find a approximation of 1 over x by some polynomial, and then evaluate it. Of course, you want higher accuracy, then you have to go to the higher order of the polynomial. And again, the base polynomials to use are Chebyshev polynomials. So you can do that, but there is a clever trick where you can use this. As long as the first case is good enough, say first decimal point is okay, you run 2-3 iterations of this and you are done. And I will just give you an example. So let's see. Okay, reciprocal. Binary number between 1 and 2. So I have to make some initial guess, and initial guess should be very simple. Okay, so I will make a polynomial which fits both the ends. Okay, so it will be what? X inverse I think this does the job. So at x equal to 1, this is our delta. The answer is 1, and x equal to 2, it is it should be half somewhere. It should give me half. So x equal to 2, yeah, okay, fine. So you can carry. So this is a good polynomial which will work for both x equal to 1 and x equal to 2, giving you a linear approximation. So you can take that as a starting ansatz. Okay. And now you want to see some convergence. So let us start at, so find, what is the time? Oh, time is up. Let me finish this. Inverse of 3/2. In between this endpoints, it is exact. So the first guess will be what? Here, so it is 3/2 minus so this is 3/4. The answer is 2/3. It's obviously rather crude. It gives you some answer. But now let's see the next step. And I have to use this iteration. So it will be 2 times 3/4 minus 3/4 times the number I wanted to invert, which is 3/2, and another 3/4. So to do some arithmetic, and let me see, 4 to 8, 32. So 32 and 9 here, and this is multiplied by 8. So 16, something went. $27. It's already getting very close to 2/3. That's one iteration. And try one more iteration, you will get 3/4 decimal points correct. So this is the power of this particular method. Its method is what is it? So it's called a second order method in terms of convergence. Yeah, I will stop here, but this is a remarkable fact that very simple algorithm and does the job very quickly. This is just for numbers, and next time we'll see how this works for matrices. And incidentally, means there are many other problems of linear algebra where such a strategy may be possible, but I don't think it is explored quite a lot. There might be open problems where this kind of ideas can be powerful.